eigenvalue goes in there and acts as the potential energy for the nuclei. But then you have this term, okay? And notice what that does. That says that chi lambda, and lambda is one of these electronic states, gets coupled to all the other chi lambdas by these coupling terms, okay? This one, I'll tell you first, this one is Coriolis. We normally neglect that, okay? And you get Coriolis in there because when you solve the electronic problem, you do it in the body frame. And that's a non-inertial frame, so when it's rotating, you get a Coriolis term. We normally neglect that one. These two are non-Born-Oppenheimer terms. They're defined down here, okay? They're related to the radial derivative of those electronic functions, because notice they depend parametrically on the internuclear distance. That basically represents some inertia that the electrons have. So when the nuclei are actually moving, they've got to drag those electrons along, okay? This looks kind of like a nuclear momentum. DDR looks like a nuclear momentum. So this is something like an extra bit that when the nuclei move, they have to drag the electron, okay? But what that does is it couples state lambda to state nu, okay? The final one down there is the dipole interaction, and you can see it also couples different electronic states, okay? Which of course is good, because when you shine a laser on there, you want something to happen, okay? So, I just want to mention a couple of things about these non-Born-Oppenheimer terms, because there's something that's actually being studied quite a lot these days in strong field physics, okay? In this problem, not in H2+, but generically in, say, an diatomic, you might have potentials that depend on the internuclear distance. Maybe you have something like this, okay? And this spot is a special spot. That's called an avoided crossing, okay? Now, what we know is that this P and this Q, they peak right at that crossing. So when these energies come together, the likelihood that you make a transition via this coupling gets much bigger, okay? That's one of the advantages of having these adiabatic potentials, is that where you see these avoided crossings, you have a chance for a transition. So you can go from this electronic channel to that electronic channel, okay? This kind of a picture really sort of evolved in the collision community. But I think you can appreciate why potential energy pictures are favored, are useful. And after all, from your first physics class, you were taught to look at potential energy and kinetic energy. Even when you took your advanced class, you talked about effective potentials, because those are useful ways to think about things. So these are effective potentials for this nuclear motion, okay? Notice, if those aren't there, and we have no field, then this is a problem that separates, okay? So you're essentially you're trying to separate these degrees of freedom, the nuclear and the electronic, okay? And that's not exact, so there has to be some coupling between them, okay? And that's what this reflects. These transitions that might happen at such an avoided crossing are called radiationless transitions sometimes, okay? They're driven by non-Born-Oppenheimer coupling. In polyatomics, and that's where the field is really interested in these kinds of things. In polyatomics, the potentials don't depend on just one internuclear distance, they depend on several. That means you have potential energy surfaces, and where those guys come together is called a conical intersection, okay? And that's where polyatomic species can make transitions without emitting any radiation or absorbing any radiation from one electronic state to another, okay? That's the importance in a broader sense, okay? So all we've done is go to a basis of these electronic states and write down our Schrödinger equation. So that's what needs to be solved computationally, okay? These guys, remember, depend on the full internuclear vector. So all the angular degrees of freedom are in there. Rotational kinetic energy is in there. So we just solve this numerically. We expand the nuclear wave function on partial waves, that gives us coupled 1D equations and the internuclear distance. Okay? For H2+, we can get rid of all of these guys, and the transitions are just governed by this dipole operator. Okay? Okay? Like I said, I'm not going to tell you the computational details, but I'm happy to answer anybody's question on that later. This is what the potentials look like for H2+. Okay? Now, we have internuclear distance and we have potential energy, so this is energy, this is in atomic units. The bound vibrational states have to live in this well, below the lowest threshold. That's where your bound states will be. Asymptotically, it's going to go to a proton plus hydrogen. Okay? But of course, this state is the 1s sigma g, so I've labeled all the sigma g states are black. The sigma u states are red, and the sigma is the angular minimum around the molecular axis of the electron. G and U are, think of them like parity. They determine selection rules when you absorb photons. Okay? But I've also shown here the n=2 manifold of curves for H2+. I've also indicated up here at 0 the ionization threshold. So this is the asymptotic ionization threshold. Okay? But what that means is that, okay, so these go to proton plus hydrogen in the 1s. These go to proton plus hydrogen in some n=2 state. Well, between hydrogen and n=2 and hydrogen, well, ionized, there's a whole infinity of states in there. So I've left out an infinity of states in this picture, right? Manifolds like this that converge to P plus H n=3, n=4, n=5, the whole Rydberg series. Okay? Yeah?
One question to your sketch there.
Yeah?
So, the matrix element has this derivative with respect to the nuclear coordinate.
Right.
So one can think about this like about the momentum.
Right.
So can one think about this whole process there like in terms of Landau-Zener tunneling? That the faster the molecular motion.
Absolutely. I mean, you can, yes. This kind of a crossing, Landau-Zener is the model for that kind of crossing. Landau-Zener was basically generated the first, they came up with it in the first place to describe these kinds of things, because it was really collision problems. Okay? Okay, so these are potential curves, and for the most part, the nuclear interaction was included so that all of this potential represents all the interaction between the nuclei. Okay? Because if we go back, this potential energy here, that's the potential energy, that's the interaction between the nuclei. Okay? And if we left out the 1/r between them, it would have to be added there and you would sum them up to get the whole thing anyway. Okay? What else? Well, dissociation, of course, is you start in the vibrational state here, you absorb a photon, and you get above this energy. Okay? And for the most part, in strong fields, what people include are only these two states. They leave those out entirely. Okay? And the reason is that between here and there is about 10 eV. At 800 nanometers, 10 eV is how many photons? 6, 7, something like that, right? So you need 6 or 7 photons to get up there. Okay? The intensity needs to be rather high for 6 or 7 photons to come into play and take you up to those states. Okay? In practice, around mid 10 to the 13 watts per square centimeter is enough intensity to start bringing these into play. Okay? These are what the dipoles look like. Remember, in our equation, what was driving transitions is this dipole matrix right there, right? This is what they look like. Normally, people only talk about that guy, which keeps going up like R/2. Okay? It's really simple, it just diverges, R/2. The rest of them, though, do come in if you have to worry about going into an n=2 manifold. Okay? Again, for the most part, that's what dominates. If you actually do calculations now, we can calculate, say, from different initial vibrational states, we can calculate the total dissociation probability. Okay? What I'm showing here is exactly the total dissociation probability as a function of intensity. Notice the scale is different in these different plots for 3 different pulse lengths. Okay? And again, what we want to test is what is the role of rotation? Well, in each of these plots, I'm showing 3 different approximations. Okay? The one that you should consider exact, the one that includes rotation, is the blue one. Okay? The blue one is circles in here. That's the exact one. If you just fix the molecular axis to be exactly along with laser polarization and don't let it rotate, which is what most people do when they do calculations on H2+. Okay? That's this magenta one. That's the triangles up here. Okay? And if you make a little more sophisticated version of that model, in other words, you take the axis to be fixed, but not just along the polarization, but every angle, and then average over all of those to represent the initial isotropic distribution, that is the red one. Okay? It's the average of the no rotation. I'll explain that just after I answer the question. Yeah?
The V equals 7, 9, and 12, what does that mean?
That's the initial vibrational state. Okay?
So what are the numbers, like 7, what is?
So vibrational states start at V equals 0. That would be the ground state.
Okay.
Okay? And for H2+, it goes up to V equals 19. Okay? That's the last bound state in H2+, for J equals 0. So yeah, V equals 0, 1, 2, 3, up to 19. And so I just picked a few of these out. Okay? We picked 9 because it turns out that's the one that dissociates the most, typically in 800 nanometer light. Okay? And these are just representative other states. Okay? You'll notice in almost every case that the calculation with the molecular axis just along the polarization overestimates dissociation probability. Okay? Which makes sense in a way because you've taken the one that sees the maximum field. Okay? Along the laser polarization, that's the maximum field. Okay? So that always overestimates the dissociation probability. And this is, in fact, characteristic of reducing the dimension of a calculation. Okay? Anytime you cut out degrees of freedom and don't represent them in any way, anytime you cut those out, I won't say anytime, most every time you cut them out, you overestimate ionization, dissociation, and all of those things. Okay? Moreover, you'll notice that these reduced dimension ones, these ones with no rotation, the dissociation probability goes up and then back down. Right? Reminiscent of the stabilization that Lars was talking about, that other people talked about long ago. In the molecular problem, that's called vibrational trapping. Okay? We'll get to that in a second. So the calculation with the fixed axis shows vibrational trapping, shows this stabilization-like behavior in many of these cases. But the exact calculation shows it basically in no case. In no case does the dissociation probability go back down in this range of intensities. However, one interesting thing is that if you take your molecular axis and average it over all those angles, it doesn't do too bad in many cases. Okay? It doesn't do too bad in many cases. The cases that it does best are the short laser pulses. Okay? And again, given our argument earlier, that probably should make sense to you. Because the laser pulse is so short, it has no time to rotate during the pulse. And in this calculation, we're just asking about the total dissociation probability. So we don't care about any rotation later. All we care about is what happened during the pulse. Does it dissociate or doesn't it? However, if you look at 135 femtoseconds, that kind of averaged one doesn't agree with the exact one. Okay? Which should suggest to you that maybe in 135 femtoseconds, this molecule really is rotating. Even though that's much shorter than the free rotation period, it really has time to rotate. And so simply averaging over a fixed molecular axis is not enough to give you a good answer. Okay? Yeah?
Can you comment then if that's why the pink is good? Because that would seem to be worse if it's rotating than the averaging over it.
Why is the peak, oh, why is
Pink
the,
one, why is it close to blue? If,
why is it close to the blue? Because in 135 femtoseconds, what happens is the molecule essentially lines up perfectly with the laser polarization during the pulse, which is exactly the model that the magenta line is showing. Okay? And if you calculate the alignment, right, the degree to which the molecules lie along the polarization, as a function of time, you can see that. I didn't put that plot in here, but that's what you see. Because you can actually see that in this case, the molecules align during the pulse. Okay? So I would say that these plots suggest, even for these short pulses, that you probably ought to include rotation, or at least the rotational average, to avoid errors like vibrational trapping. I put errors in quote, but because it's something that you get misled into believing if you look at these reduced emission calculations. Okay. Now, vibrational trapping, does anybody know what vibrational trapping is, or why people even expected it? Okay, well, let me take one more trip to the whiteboard, and I'll answer Lars' question from the other day about talking about Fouquet. Okay, because when Phil was doing measurements on H2 plus back in the early days, they saw a lot of these phenomena that I'm talking about, and they explained it with this picture called Fouquet. Okay? And it's based on taking these Born-Oppenheimer potentials. Of course, in H2 plus, they look like this. Okay? Fouquet, can everybody see this color? The marker doesn't look so good. Fouquet is a way to take advantage of the periodicity of the laser field to do some mathematical manipulations. I'm not going to explain the math. I'll just tell you the recipe for what you do. Okay? You dress the potential curves by some number of photons. So you would take this 1s sigma state, say with some vibrational state in here, we'll call that 0 photons. Okay? Now, when you absorb one photon, you have to go to the 2p sigma u state. So this is 1s sigma g. This is 2p sigma u. Okay? And I wrote that in an unfortunate spot. Okay? So this one is 1s sigma g. Fouquet says you dress this, so you move this one down by 1 photon. So that would be n equals 1, and that spacing is exactly omega when h bar is 1. Okay? Now, you dress the 1s sigma g down by 2 photons, so that spacing is omega. And you do the same, you dress 2p sigma u down by 3, n equals 3, so there's omega. And you keep doing that. You just keep shifting these down, making more and more copies of this. Okay? We know that the 0 photon and the 1 photon curves are coupled by the dipole matrix elements. Okay? So that means that there's coupling right there. Okay? There's coupling right here. Now, the 0 and 3 photon curves aren't directly coupled by a dipole matrix element, but they're coupled by a 3 photon transition, so there's an effective kind of coupling here. And the idea, and you can write it out, maybe I'll do that in my last lecture. You can write out a matrix with all these dipole couplings, you diagonalize that matrix, and what that gives you are Born-Oppenheimer potentials with the effect of the field included. Okay? What that does is it makes an avoided crossing here, just like I sketched before. You have a non-adiabatic transition possible here. Okay? You also get an avoided crossing there and an avoided crossing there. Okay? So those are your new potentials. When the field is on, these are your new potentials. So this vibrational state would tunnel through the barrier here and dissociate, and that would be its kinetic energy. Okay? By the way, molecules don't really tunnel. Nuclei don't tunnel. Okay? They're too heavy. They can't tunnel very far. So the lowest one that really gets out is the one that's right at the top of the barrier. So it will come out and have that much kinetic energy. However, we started with vibrational states all the way up here. So some of these actually get caught in this well that forms out there. Okay? Those are said to be vibrationally trapped. Okay? Because if they're trapped in the well, they can't really get out here very easily. So it's expected that those states won't dissociate as much. The dissociation probably won't go down. So that's this picture. V equals 12. V equals 9 is right here, right in the middle. That's why we showed V equals 9. It's right in the middle. So when the field turns on, it comes out immediately. Okay? V equals 12 is up here. And you can see it shows all this crazy stuff. By the way, in this picture, there is no angle. This picture is drawn assuming the molecular axis lines up perfectly with the laser polarization. Okay? And so, in a sense, we've done the same reduced dimensionality trick that we did to get this magenta curve. Okay? And so people expected vibrational trapping. Yeah?
How does your picture depend on the intensity? So you get this oscillation?
This gap, at a fairly simple level, is related to basically it's 2 times the field. Okay? So as the field grows, that grows. It's not quite so simple as that, but qualitatively, yes. As the field grows, that gap gets bigger. I'll show you a picture in a minute. Just exactly how it looks. Okay? So people expected vibrational trapping, and they saw it in their calculations. Everybody was happy. Okay? Except that when you actually include rotation, it seems to go away. And people found that out long before we did these calculations. We weren't the first ones to say that.
Why is that?
Why is what?
Why do you move the technique have routine?
Oh, well, one answer is when you include rotation, there's another way for it to go. So the ones that get trapped here, they can sneak out another way and dissociate. Because they can turn and get away. Okay? And that's generally what happens when you go from the reduced dimensionality to higher dimensionality. Because as you can see, these other possibilities for happening changes things dramatically. Another reason that folks expected vibrational trapping or talked about vibrational trapping is because when they plotted dissociation probability, say the total dissociation probability, as a function of V, when they did this calculation without rotation, they saw, for instance, this big dip right here. Okay? So dissociation probably goes up. It's almost 1 for these intensities. But as you get up to V equals 12, which again sits up here, which you expect to be vibrationally trapped, you see this big notch, you see this big dip. It doesn't dissociate. Great, vibrational trapping, that works. Okay? And you can see that as you go from 10 to the 11, which is this one, to 10 to the 12, that one, you can see such behavior. And you can see these states, in fact, the higher intensity has a lower probability. Okay? This is the calculation we did with rotation. And you can see the increase is just simply monotonic. But you do still have a dip there. So how do you understand that dip? Is it really vibrational trapping? Maybe it's still there. Well, if we do the calculation in first order perturbation theory, okay? Because all of these states can dissociate with 1 photon. If we just calculate the dissociation problem in first order perturbation theory, we get the red curve. Okay? So the reason there's a notch there, the dipole's small. There's simply no dipole to dissociate from V equals 12. It has nothing to do with multi-photon effects, it has nothing to do with vibrational trapping, which is a multi-photon effect by definition. Okay? It simply exists, or doesn't exist, as dissociation, because there's no dipole. So this is one important thing to remember. Even though you're doing strong field things, especially when you're doing it with nuclei, don't forget to look at what first order perturbation theory gives you. Okay? Because at the very least, when you see deviations from first order, you know that's multi-photon for sure. Okay? So, we're getting a little bit late, so what do I want to show here? We can look at angular distributions. So if you want to talk about, and then the other approximation, we talk about geometric alignment. So if you have laser polarization, and you have this isotropic distribution of molecules, Geometric alignment, remember, is that those molecules in this direction will dissociate. If that's true, then if you look at the bound part, you should see holes start to develop in the bound part, right? The distribution should get pinched. Well, if we look at V equals 6, V equals 9, and V equals 16, in this kind of a laser pulse, 5 femtosecond, 800 nanometer, let's see, T1, that's just this, let's see, black dashed line. That should be isotropic. I don't know if the aspect ratio looks like it, but the black dashed line is isotropic. At T2, right, you should start having some dissociation. That's this one. It's actually, okay, it's a little flatter, so maybe you're, oh wait. Oh, that's no good, because the polarization is this way in the pictures. So you actually don't have a hole there. It's going the other way. Well, okay, that's not quite what we expected. This blue dashed line, oh, it's not much different. And at T4 at the end, you see it's actually aligned with the field. But really, there was no place where holes got burned in there, okay? Which I would say is evidence that there's not much geometric alignment in V equals 6. Now in V equals 9, you can see that there is a deficit along there for the red one at T2. So a little bit of the things along that direction did get dissociated, but it quickly recovered to fill that out, okay? And again, you can go through these pictures, and because of time, I won't go through all of the details, but there's no drastic evidence, there's no sort of dramatic evidence of hole burning in these, which would seem to indicate that there's not much evidence for the geometric alignment here. It's true that when you measure the final distributions, it tends to be aligned along the polarization. But that doesn't mean that you preferentially dissociated the things that were started along the polarization. That just means they ended there, okay? I'll just explain what this is about. So one argument would be that, okay, H2 plus is the lightest molecule, which means it rotates the fastest. So if there's going to be a geometric alignment, if there's going to be hole burning, maybe it's not going to be on the one that rotates the fastest, but maybe on something that rotates more slowly. So if we just simply increase the mass from H2 plus to T2 plus, and then to a fake O2 plus, we kept the same potentials, we just increased the mass artificially. Theorists can do that, okay? You don't see any real dramatic differences, okay? There's still no strong evidence of this hole burning or geometric alignment. That raises the question about axial recoil. Axial recoil, remember, is, okay, we're done with the pulse. Do the fragments just go on a straight line to the detector? Or do they maybe curve and rotate on their way to the detector? Okay? And so one way you can look at that, and again, we can only do this in theory, is we can calculate the angular distribution at the end of the pulse, T final, that's the red ones, and the angular distribution at T equals infinity, that's what you would measure in your experiment. And you can see that this is, okay, 10 femtosecond pulse, 5 times 10 to the 13 watts per square centimeter, 10 to the 14, and a 5 femtosecond pulse. And you can see that the angular distribution actually changes rather dramatically from the end of the pulse to T equals infinity. Okay? If you quantify that by calculating the alignment, which is calculating the width of this distribution, that's just expectation value of cosine squared theta, then you can see down here as a function of intensity, the relative change, which is the, I don't know, pinkish purplish circle one, the relative change in cosine squared theta from the end of the pulse to infinity gets up to about 10%. Maybe, I don't know, well yeah, over here. Gets actually above 10%. But folks that are doing alignment, that are purposely trying to align molecules, have worked really hard to get a 10% relative change. That's actually a very big change in the alignment. Okay? And that's what you can see in these kinds of plots, that the change is actually fairly dramatic. Won't go through that one, but I do want to show this one, because this actually gets at the same kind of question. Okay, hydrogen is a light molecule. Maybe it's just rotating faster because it's so light. Well, what if we artificially